Okay, this is a short video. I'm just going to go over the Chapter 7 stuff, the step response for RL and RC circuits. So these are circuits consisting of a single inductor or an equivalent group of inductors simplified down to one inductor and a resistor. And these can be in various configurations. But anyway, there's going to be a resistor, an inductor, and a capacitor, and a reductor in different series and series and parallel combinations. But the basic idea, what's going to happen is there's going to be a signal that's steady state, and then a switch will open or close, and this signal, it's either going to be a voltage or a current. It's going to reach a new equilibrium, and so this is like t less than 0, and then this is t greater than 0, and then at 0 a switch closes and these things just decay down like that. And this is e to the something, and I call this exponential decay envelope. So if they start out and decay down to 0, we call this the natural response. And if they start out at some other quantity, could be 0, but the more general case is they start out at one quantity and go up to another quantity. It could go up like that, or it could go, down like that. This is the step response, which is the more general situation, and this appears called the natural response. All right, so I'm just going to point and talk about these at these notes that are already posted for step response. So you might want to pull these up and follow along while I'm doing this. Go ahead, you can do that now. I'll wait for you. Okay, great. So yeah, natural response of an RL circuit. So we're talking about natural response, which is the behavior when they are allowed to naturally de-energize down to 0. So there's two parts to the circuit. There's one part is the energizing circuit that gets this element up to a certain energized state. And then the switch will, in this case, will open and disconnect the energizing circuit from the decaying part of the circuit, and then we'll just watch in this case, it's going to be an I signal decay down to 0. So I sub S, I sub source, is a constant DC source, and there's this R0 resistor in here, which you may or may not need. Generally speaking, depends on the nature of this power supply, if it's a battery or could be other things. So you might not need this R0. And then this RL is the load resistor, the element that's going to take the energy that's stored up in this guy here and use him up, turn him into heat. So let's see, yeah, there'll be a current I, little I through L, and then there'll be a voltage across this resistor with this polarity, the voltage V. So the switch has been closed for a long time. All right, that's what we mean by that is long enough for the current in this inductor to reach essentially a steady state. So that depends on the size of the inductor, but eventually, if you leave this switch closed for a long time, this will get to a steady state. So at that steady state, the current I through this inductor will be constant, and it will appear as a wire because the current is non-changing, right? If it's constant, after a long time, it's constant. It's non-changing. That means the derivative is 0, and since the voltage is proportional to the derivative of the current, the voltage will be 0. So it'll appear like a wire because it has 0 volts across it and this current through it. And then because this is appearing as a wire, the resistor that's in parallel here will be shorted out, and it will not affect the circuit. So I've drawn this as a dotted line to show that it's not affecting the circuit, and I've drawn this inductor as a dotted line to show that it's behaving as a wire. So at this condition, all the initial current in I sub s runs through the inductor. The R's disappear, so to speak. That is, they don't affect the circuit. Here's a note on if R0 is needed. Don't worry about that, really. Okay, so after the circuit's been closed for a long time, the current little I is basically big I sub s. It's the current in the inductor is equal to the current in the source over here. So then we throw open the switch, and this t equals 0, the switch opens, and the left side of the circuit is disconnected from the inductor. And then the inductor will discharge over time. It'll discharge its energy to this resistor here. So this is for t greater than 0. So we know the quantities we're interested in is what is I doing, what is V doing, what is the power that's delivered to this resistor from the inductor to the resistor and turned into heat, and what is the total energy discharged from the inductor and turned into heat by the resistor. So we know these answers in general are going to be of this form. All right, so the I as a function of time is going to be the initial current in the element, in the inductor in this case, times e to the minus t by tau. And tau is L over R. It's the inductance over the resistance for an inductor. And let's see, back to I. So I will have this shape here. It'll have an initial current in it, and then it'll decay down to 0. We call this the natural response when it decays down to 0. So the inductor fully de-energizes, and the current before 0 will be I0, and we would expect that because inductors cannot have a step change in current, but they can have a step change in voltage, and you see that here, and that should make sense because when this guy has a constant current in it, the derivative of the current is 0, therefore the voltage is 0. So that's what this is indicating here. So less than 0, the voltage is 0, but then as soon as you throw the switch, the voltage jumps way up to some quantity and then decays naturally down to 0. The equation for V is just from Ohm's law, really, because we're discharging to a resistor. Right, we're discharging this inductor to this resistor. So by Ohm's law, V equals I R. We have this expression for I, so just throw R in there. That's this guy. That's where V comes from. Okay, P is just IV. P equals IV. So you multiply these two expressions together, and you get this I sub 0 squared R e to the. You'll add the exponents, e to the minus 2t by tau. So the power will decay faster, and it'll have a step response because voltage is initially 0. So 0 times any I will be 0. The initial power will be V and I, V times I, and then it'll decay twice as fast. Then the energy we're using our general formula here, 1/2 Li squared, but because I is a function of time, there's this in here. Now here, this is from the perspective of the energy delivered. So in this circuit for t greater than 0, this thing gets charged up to an initial state by the left-hand side of this thing, and then it delivers its energy to this. So sometimes you'll see curves that start at 0 and go up, or start at some maximum value, go down. It's really, if it's down here, you're talking about the energy that the resistor receives. So you could say that it's the energy delivered by the inductor. So it starts at 0 and goes up to some value because, you know, we're delivering to the resistor. It's not, you might see a curve that starts like this and then goes down. Then you're a W curve. Then you're talking about the energy in the inductor, right? It's at some initial value. It's charged up. The inductor is charged up, and then the energy is delivered. So this form with the 1 minus e to the minus t 2t by tau is from the perspective of delivering energy from the inductor. If you just took out the 1 minus, then it would be from the perspective of receiving the energy from the this is from this is delivered by. I'm getting a little confused here. I'm just going to move on. One is, you know, one either goes up like that, and then there's another one that comes down like that, and you can take the E out, and it's from the point of view of delivery or receiving. Anyway, so tau is L by R. Yeah. Okay, that's what we call the natural response, in this case of an RL circuit. RC is very similar. So we have an energizing part of the circuit on the left, and in this case it's a voltage source, and it's going to charge up this capacitor with a certain voltage. Then we're going to throw the switch and disconnect the capacitor from the energizing side of the circuit and discharge it over time to the resistor. So we're going to discharge the energy in the capacitor into the resistor. So you solve it similarly. You solve it or you redraw the circuit at two different times, t less than 0, and then t greater than 0. So for t less than 0, the switch has been closed for a long time. When you do that to a cap, the voltage will match the source voltage. That is, the voltage in the cap will be constant. And because it's constant, that means the current, remember for a cap, the current is the derivative is proportional to the derivative of the voltage. So the current will be 0. And the cap, which is still here, but it's it's behaving as if it were an open circuit. You could draw it like that. Because caps are open circuits. I mean, caps don't. There's an insulator in here. They don't conduct through. You know, this doesn't happen. The current does not conduct through here. The current kind of comes from the plate. It goes to the plates and stops and leaves the plates. So it doesn't go across. So they are an open circuit for steady state, and that's exactly how they behave for steady state voltage. All right, so for the switch closed for a long time, the cap will appear as an open circuit, and it will match the voltage of the source. So when we throw the switch, throw the switch, we disconnect the energizing part of the circuit, and now we're discharging the cap into this resistor, and the circuit looks like that for the discharge phase. So the V sub S is the voltage in the cap. The cap is charged. It has a certain amount of energy in it, and that energy is going to dissipate through this resistor and be turned into heat. And the 4 signals that we're interested in are voltage, current, power, and energy. And this is the voltage signal. It's steady state for t less than 0. And then we throw the switch at 0 and it decays like this. I is 0 before the switch is thrown, because this thing is a constant voltage across it at steady state. The current will be 0 for a constant voltage in a cap. But then you throw the switch and I will jump up to this value and then start decaying. That's these two equations. So voltage is the initial voltage, V0. In this case, V0 is Vs. But the initial voltage then this decay, exponential decay envelope, e to the minus t by tau, where tau is RC for an RC circuit. And by Ohm's law, I is V over R, so you take this V equation and throw R on the bottom, and you got the I response, the current response. Multiply these two guys together, you get V squared over R e to the minus 2 t by tau. That's this thing. And then here's the energy equation from two perspectives. If it's absorbed by the resistor, then it's this term has here, this decay envelope term has this funny shit, has this format, and if it's delivered by the cap, it has this format. But it's a variation on our general energy equation, 1/2 CV squared. It's just that V is a function of time here. And then here here we're showing absorbed by the resistor. So it starts out at 0, right? The resistor has no energy in it. And then over time, the resistor absorbs some energy. And the other equation would be, the cap has energy in it, and then it delivers it to the resistor. It would just be the mirror of this thing. Okay, that's natural response for an RL circuit and an RC circuit. There's a more general case where they don't necessarily start well, they start at somewhere and they go to somewhere else, and that somewhere else doesn't necessarily have to be 0. So they go from some initial value to a final value. They either start at some high value and drop down to a final value, or they start at some lower value and go up. And these upper and lower values, one of them could be 0. So it's a more general case of the natural response. All right, so keep in mind that an element may have a step change in the current for a cap or the voltage for an inductor. And so there's an initial state and a final state, and there's an what I call an E response, this e to the minus t by tau response between the initial and the final state. And for an RL circuit, the current response for an RL circuit, we will be solving for the current response to a step change in voltage. And for an RC circuit, we will be solving for the voltage response to a step change in current. And so we have a general solution. We just use X, so we can apply this solution to caps and inductors. So X will be either I for an inductor or V for a cap, all right? And then this tau thing will be RC for a cap and L by R for an inductor. So this X of t is just the final value plus the initial value X of 0 minus the final value X of f, quantity times e to the minus t by tau. And we know the solution is going to look like this for circuits of a certain type. And so this is a shortcut, so we don't have to do calculus on all this stuff, right? Because if we didn't, we know what the solution is going to look like, so we just construct it. We just solve for the initial value at t much less than 0. We solve for the final value at t much greater than 0. We solve for tau, which is RC or RL, and then we just plug into this stuff, and we don't have to do, a lot of fancy math to get these equations and then solve them, which would be a lot harder. We're just going to do this shortcut thing. And yeah, the other thing I could say is that we're going to take some element, in this case it's a capacitor, and discharge it through a resistor. Sometimes this will be guess what, the equivalent resistance of a larger circuit, kind of like the Thevenin resistance. All right, so that's this video. I will work some problems now in other videos. Thanks.